Okay, new era for me. I'm gonna start working on my weak points. One of the big ones being dynamic programming. I don't know why. I've just always kind of struggled with grappling it. I understand it in concept, but when I try to actually put it down into writing, I struggle. So I'm gonna fix that. I'm gonna change that. Given n pairs of parentheses, write a function to generate all combinations of well-formed parentheses. So, dynamic programming is the concept of essentially building up your solution or building down your solution because of overlapping subproblems. So, for example, the Fibonacci sequence is good dynamic programming because the solution to one number is the solution to the two prior numbers. So that's like tabulation. You build it up as you go. It's like because in order to solve what the 20th number of the Fibonacci sequence is, you need to be able to solve the 19th and the 18th. Because Fibonacci sequence, each number is the sum of the prior two numbers in the sequence. And this is listed as one. Generate parentheses. Given n pairs of parentheses, write a function to generate all combinations of well-formed parentheses. For example, if n is 3, then we could have open, 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 close, close, closed, open, 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 closed, open, closed, closed. You know what I mean. So on. So how do we make this dynamic? Do we build it top down or bottom up? Do we try to build like a matrix? Because if we have, let's see, for n equals 1, we know that we could just do that. For n equals 2, we could do this, this, or this, and that's it. Okay, so n equals 2, I did attempt this a while back, and there was like one condition that I didn't get to. So how do we build this up as subproblems? Because n equals 2 is like n equals 1 plus n equals 2, or plus n equals 1. Or n equals 1 surrounded by parentheses. Okay? So n equals 3 is n equals, you could have open, 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 or a bunch of pairs. You could do this and that. You could do the opposite. Or you could just do open, 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 close, close, closed. And what are these? Well, we have n equals 1 times 3. Or we could do n equals 1 plus n equals 2 2. Or we could do the opposite of that, n equals 2, 2 plus n equals 1, or n equals 1, or 2, 2, surrounded by parentheses. Okay, so I think I'm starting to see the pattern here. And this really is n equals 1 plus n equals 2, 1, because it's this one. So right now I'm thinking it's sort of like a 2D array. We have this DP table that's like a 2D array. And that 2D array, the first index is the number of parentheses. The second index is the different types for that one. And then to solve it, we just calculate out all of the we just calculate out all of the combinations. So if we have like n equals 8, well, that could be n equals 7, 1 plus n equals 7. Let's just start saying n1, n7. It could also be n2 plus n6. And so on. Do we have to worry about multiple types of combinations? No, because those are all covered by the subproblems. So we don't have to worry about n, because like, look at this. Like, if we have n equals 3, we don't have to worry about doing n equals 1 plus 1 plus 1, because 2 already has all of the 1 combinations covered. So we build it up over time. Okay. So here's my strategy. Start at n equals 1. Or have base case of n equals 1. Build up dp I j from there. I is the n value. J is the combination of parentheses. Okay, so like this right here. We have n3 in the table. It would be 3, and then 3, 0 would give you this. Okay. So let's make that happen. Let's start by making the table dp. We could just make this be, what was it? Well, no, that's, yeah. Let's, dp equals, oh, what is it? It's a 2D array. And we could start by, and we could just say this times 8, because we know that n is going to be no more than 8. Cool. So now we can say that dp1 equals, no, sorry, dp0 being n equals 1. Oh, yeah, dp0, which is n equals 1. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Would be open just this. Okay. Cool. Now, we're just going to build it up over time And we don't need to go anything beyond n. So we're going to say for I in range, because I is the n value, in range n plus 1, because we're going to include that it's inclusive, because range is exclusive for the upper bound. For I in range n plus 1. Now, actually, we can start with it being 2. Nope, 1. Okay, so because it's 0 indexed, but n starts at 1 and ends at 8. So actually, we just do until n. Because let's say that n was 8. We already get the 0 index, and then this would give us 1 through 7 because we have 1 to 8, but the 8 is exclusive. Okay? Now, time to figure out all the combos. Find all pairs that add to n. In order to do that, so we're not going to include 0 plus 2. So for example, e.g. with 3, that is 1 plus 2 or 2 plus 1. We're not worrying about 0 plus 3. Because we don't know, because 0 doesn't give us anything. And we're trying to find what 3 is by adding up the subproblems. So we're going to say for let's see, I don't want to use J. X in range 1 all the way up to I. If that'll work, because if I is 3, for example, then that gives us 1 and 2. Okay, now is X second subproblem is I minus X. Okay, so if we have 3, then that gives us 1 and then 2, and then X goes up to 2, so then we get 2 and 1. But I is actually going to be 1 lower than n, so we need to do I plus 1, because that gives us 1. Because for the for the second iteration, I is going to be 2, so we need to bump it up by 1. So X starts at 1 and goes up to 2, because I is 2, plus 1 is 3, exclusive is 2. Yes. That'll give us all the combinations. Okay, now do we want to just hard code the second problem? Because this way we can make sure that because I'm now realizing, yeah. dpn minus 1. That's going to be the answer. I'm realizing that we need to do this. There we go. Because we need at least 2 subproblems to make the next problem. And those are pretty straightforward answers. And those will be the answers to 0 and 1. So we've already solved a couple of the problems. Okay. Second subproblem, I minus x plus 1. First subproblem, x. Second subproblem, I minus x plus 1. Okay, now we're going to say we need to iterate through all of the answers for the first subproblem and the second subproblem. So we're going to say while a is less than dp dp0, or no, dp first subproblem, and b is less than, oh, sorry, the length of those. We're just going to say first and second. First, and b is less than the length of dp second. No, we just do a 2D array. A nested loop. That's the same. It's the same. For F answer in first, for S answer in second, dp I append F answer plus S answer. Finally, we need to worry about the wraparound. So we're going to say dp I append Actually, when does the wraparound come into play? The wraparound comes into all of the S answers So we also need to worry about the wraparounds. So that would just be 2, all of the 2 answers. Yeah. So we could say for answer in DP I feel like I'm going crazy, but this would be awesome if this worked. DPI, append, and then we're just going to do those wraparounds where we okay, because for 3 we have, this is n plus 2 plus n1, this is n1 plus n2, this is n1 plus n2. There are going to be some repeats that we have to cut out. And then this is N2 wrapped, and this is N2 wrapped. Okay. Wait, I actually think that's the answer. Oh, wait, no, it's not. We need to get rid of the repeats. And we can do that. We don't accumulate repeats. I'm just going to look up a quick solution for this. Set, that's right. DPI equals set DPI. Okay? Eliminate duplicates, because there will be some duplicates. For example, this is n plus 2 plus n2 plus n1, but it's also n1 plus n2. Okay, let's comment this out. Find all pairs that add up to handle that add up to n. For example, 3 is 1 plus 2 or 2 plus 1. Handle wraps by adding open and close around prior answer. Go through increase first problem and decrease second to get all combos. Is this it? That'd be crazy if this was it. I'd be so happy. Let's try it. Huh? How do you do? Okay, yeah, I was doing it too simply. Sorry, I had to look that up. For in range, and we can actually just say n. N. No, we'll do 8 because if you get 1, if the answer if n is 1, we don't want to try to assign DP1. Memory limit exceeded. How is this memory? I'm just confused. I'm sorry as to why this is taking so long. I'm not confused as to why this is taking so long. I'm confused. I mean, I know that I'm getting duplicates here. Oh, okay. I looked it up. And I found a great point. A great point. Instead of doing the wraparound of the answer before it, just do the wraparound when you add them together. And to make this work, you actually have dp0 just be empty parentheses. Thereby, when you do the wraparound, no, but maybe it's that we keep on accessing the 2D array over and over. So actually, what if we tried saying new row equals an empty array? And now we say new row instead of DPI. Now DPI is the set of new row. Would that work? Well, it didn't work for, I mean, I didn't add the new test case, but please work. Please work. Wrong answer. Okay, so this only did the wraparounds. So that means that something didn't happen here. Yes, it is because I set this to, I oversaw it. there's no need to increase I should have just done range of I, because the DP, it doesn't matter what n is. We already, the DP array, sure, n starts at 1, but the DP array starts at 0. And that's what happened. Let's see if it works. Awesome. So I need a little bit of help there, but I got most of the way on my own. Great problem, and I have attempted that before, so to beat it finally is very satisfying. The problem with my answer came down to a couple of things. Because I kept on accessing the 2D, the array within the array, as opposed to just making a new array and then setting that at the end, it used up a lot of memory. The other thing was that the index was wrong because I did +1 instead of, and starting from 1, and so as a result I was accessing one row later in the table than I meant to. All right, great problem. Thank you for watching.